Welcome again to the second lecture in this course of the heat transfer. In the previous lecture, we illustrate the general heat conduction equation in Cartesian coordinate, which is del square T plus Q divided by K equal to 1 by alpha shal T shal tau. In the general heat conduction equation, we illustrate that the temperature in three-dimensional coordinate, which is the shal square T shal x square plus shal square T shal y square plus shal square T shal z square. These terms illustrate that the temperature change in x, y, and z plus heat generation. There is some bodies will have internal heat generation inside this body, like the nuclear reactor divided by K equal to 1 divided by alpha, and alpha is the thermal diffusivity, and we illustrate that alpha is K divided by rho Cp, thermal conductivity, density, and the specific heat at constant pressure, multiplied by the temperature variation with tau. This is the general heat conduction equation as I illustrated in the previous lecture in Cartesian coordinate. However, we can make some simplification, for example, in this equation, so that one of these simplification, we can write that for a steady state, we know for a steady state that there is no change with the time, so that the temperature will be constant with time, so that this term of the right hand side will be equal to 0, shal T shal tau equal to 0. In this way, this equation will be simplified to this equation, shal square T shal x square plus shal square T shal y square plus shal square T shal z square plus the heat generation term divided by K equal to 0. If I want to describe this equation is the general heat conduction equation in a three-dimension x, y, and z with internal heat generation. Okay, for example, if this is our control volume, there is some amount of heat generation will be generated inside this control volume, so that this equation that governing this situation will be something like this. However, we can make a lot of simplification. For example, we can write the general heat conduction equation, which is this equation. Okay, let us write it for any steady state. Okay, so that this term will not be 0, but with the without heat generation. In this way, with no internal heat generation, the general heat conduction equation will be like this. Okay, for simplicity, shal square T shal x square, and this three term can be written like this. Okay, so that del square T plus the heat generation term will be 0 divided by K equal 1 by alpha shal T shal tau. Without internal heat generation, then this term will be 0. In this way, this equation reduced to del square T equal 1 by alpha shal T shal tau. Okay, the temperature here is changed with x and y and z. Okay, more simplification can be take place. For example, let us write the general heat conduction equation. Okay, for a steady state. Okay, for a steady state with without internal heat generation. In this case, we have the following. For a steady state, then the temperature will not vary with time, so that this term will be 0, and if there is no internal heat generation, then this term will be 0. By this two assumption, the general heat conduction equation reduced to this, okay, which can be written shal square T shal x square plus shal square T shal y square plus shal square T shal z square equal to 0. This is called the heat conduction equation in three dimension, okay, which is known as Laplace equation, okay. For example, for a steady state, if we write for a steady state for two-dimensional, okay, this is for three-dimensional, for two-dimensional x and y, then this term will be 0. In this way, we will have shall square t shall x square, this equation known as Laplace equation, equal to 0. Okay, sorry, this is y. And now let me tell you something that as we go in the lecture of the heat transfer, and in the next lecture, we will illustrate that how can we solve this equation, okay? For example, this is Laplace equation, and for example, this equation also, which is the general heat conduction equation. We will illustrate how can we solve this equation numerically, because actually the exact solution actually is relatively difficult, so that in the heat transfer and the fluid mechanics, we prefer the numerical method. I mean by numerical method like finite difference method, finite volume method, okay? However, in this course, we will focus on the finite difference method, okay? We will take explicit finite difference method, explicit, implicit. I will illustrate them when we get to this subject. Also, the Crank-Nicolson, a lot of scheme for using finite difference to solve the heat equation. We will illustrate this equation in its time. However, let us here in this lecture focus on the heat equation in Cartesian coordinate. As I illustrate that this is called Laplace equation, which is very important in the heat transfer. For one-dimensional, if I want to write for one-dimensional, this is very important, for one-dimensional steady state without internal heat generation, then the general heat conduction equation will reduce to del square t del x square equal to 0. This is called the heat equation in a one-dimensional only for a steady state, so that we can write for a steady state, but for transient or unsteady state, then this equation actually for one-dimensional, then there is no y and z, and without heat generation, then this term will be 0. Since we want to write the heat equation for unsteady, then this term will not be 0, okay, because the temperature is changing with time, so that it will not be constant. In this way, for one unsteady one-dimensional heat equation will be something like this. I will write it in a partial form, because the temperature here actually dependent on two variables, which they are the x distance and the time, shall t shall tau. Here I write in exact differential, because the temperature is dependent only on one variable, while here in the partial formula, because the temperature is a function of x, and because the temperature is a function of x and tau, time, while here temperature is a function of x, which is the distance only. In this way, we illustrate the heat conduction equation, and we illustrate how can we derive the heat conduction equation in Cartesian coordinate, so that the general heat conduction equation, shall square t shall x square plus shall square t shall y square plus shall square t shall z square plus the heat generation term divided by thermal conductivity 1 by alpha shall t shall tau. This is in Cartesian coordinate. A similar equation can be derived in the same techniques. If you remember, in the first lecture, we take a control volume and we derive the heat conduction equation in Cartesian after we are doing energy balance. So that in a spherical coordinate or in a cylindrical coordinate, we can use the similar techniques in order to derive the heat conduction in cylindrical coordinate. However, I will write only the heat equation in cylindrical coordinate, which is shall square t shall r square, because in the cylindrical coordinate we have r and phi and z, plus 1 by r shall t shall r, plus 1 by r square shall square t shall phi square, plus shall square t shall z square, plus the heat generation term divided by thermal conductivity equal to 1 by alpha shall t shall tau. This is in the cylindrical coordinate. While, and finally, the heat equation for a spherical system, okay, the heat equation will be like this. Let me write the heat equation in the spherical coordinate will be this. 1 by r square sine square theta shall square t shall phi square, plus 1 by r square sine theta shall theta, for sine theta shall t shall theta, plus 1 by r square shall r, for r square shall t shall r, equal to, plus the heat generation term divided by k equal to 1 by alpha shall t shall tau. This is the heat equation in cylindrical, in Cartesian, cylindrical and spherical system. We can actually derive this equation in the same techniques that we use to derive the heat equation in the cylindrical system. So that now we will illustrate the following. We will take this equation in Cartesian coordinate and we actually make simplification. For example, as a beginning, we will consider only for one dimension. After that, we induce and included the heat generation term. And after that, we can use finite difference method to solve the unsteady one-dimensional heat conduction equation. Okay. After that, we can use the similar procedure for Cartesian. We will apply it for the cylindrical and spherical system. However, as a beginning, I will make only the one-dimensional formula of the heat conduction equation and apply it for plane walls. After that, for the cylindrical system, cylindrical pipe, for example, and for spherical system. After that, I will include the heat generation in each case. So that let us firstly focus on the heat generation, heat conduction equation in a plane walls. So that let us write the heat conduction equation shall square t in a Cartesian system, shall x square plus shall square t shall y square plus shall square t shall z square, plus the heat generation term divided by k equal 1 by alpha shall t shall tau. Now I will make the following, okay? Since our subject will be the heat conduction through a plane wall, okay, we will make the following assumption, okay? Let us imagine that this is a plane wall, okay? This is a plane wall, okay? Of course, in the previous lecture, I illustrate for you that each material have some value of the thermal conductivity, so that for one dimension heat equation, okay, so that for one dimension there is no change of temperature with y and z, because we have one dimension, then this term will be 0. Let us consider there is no internal heat generation, so that this term will be 0 also. And of course, let us make the following assumption, which is our case study is steady, so that this transient term of temperature will be 0. So that based on this assumption, which is one-dimensional, steady state, there is no heat generation. In this case, the heat equation will be deduced to the following equation: d squared t divided by dx squared equal to 0. This is the one-dimensional heat conduction equation. Now we will make the following. in the heat transfer subject, we are actually interested in finding the heat conduction equation and find the temperature distribution. So that in order to find the temperature distribution, we will solve this equation. So that I will write now the following. This is actually second ordinary differential equation, and it is homogeneous, so that it can be solved easily. I will make the solution of this, which is dt by dx equal C1. After that, this is first ordinary differential equation that can be solved easily using separation of variable, so that dt equal to C1 dx. I can integrate each part separately till I get t as a function of x equal to C1 x plus C2. Now this is the general solution for the heat conduction equation. Okay, for the heat conduction equation in a one-dimensional flow. Now we actually work on this plane, so that let us assume that there is some boundary condition. This is x, as I illustrate here, x equal to 0, so that and at x equal to 0, the left side wall is kept as T1, and at x equal to L, then T equal to T2, okay? And after that, I can actually, in order to find the temperature distribution, then this coefficient, which is C1 and C2, we must know its value, so that actually I will make the following. The boundary condition, okay? Actually, this technique is very important in the heat transfer. All you have to do after you derive the heat equation and made assumption, and you find the governing equation, then after you solve it, okay, and you will get the general solution. Then it is necessary to apply the boundary condition, so that you can find the general solution with known value, so that I will apply boundary condition at x equal to 0, then t at x equal to 0 will be T1. Now at x equal to L, which is here, then t will be T2. Now I will apply the first boundary condition. For example, this is I and this is double I. At x equal to 0, then t at x equal to 0 equal to C1 multiplied by 0 plus C2. All I have make is that I substitute x equal to 0 here at this equation, so that when I apply this, then I get that t at x equal to 0 is T1, okay, which is the temperature here. Temperature at x equal to 0. So that I get that t at x equal to 0 is T1 equal C1 multiplied by 0 is of course 0 plus C2. In this way, we can get that C2 equal to T2. Now I will sub C2 in the general solution, so that I have the general solution will be something like this, plus T2, C1x plus T2. Then I find C2. Now let us find C1. And C1 is very important, so that all I have to make is that I will make the following. At x equal to L, okay? At x equal to L, I will sub the second boundary condition here at the general solution equal to C1. X here is L, so that I will replace this x by L plus T2. So that temperature at this wall at x equal to L is T2. So that I will write T2 equal to C1L plus T2. Sorry, I make mistake here. C2 equal to T1. Okay, sorry. Because this is T1. I make mistake here and write instead of T1, I write T2. Okay. C2 equal to T1. Then this will be T1. This will be T1. Okay. Sorry for this mistake. Now I will transfer this T1 to the second side, to the right side, to the left side, so that T2 minus T1 equals C1L. In this way, we get that C1 is equal to the T2 minus T1 divided by L. Now this will be substituted in the general solution, which is this, so that we get the following. Tx equal to c1x plus t1. T as a function of x. C1 is t2 minus t1 divided by L multiplied by x plus t1. In this way, we can find the general solution of one-dimensional heat conduction equation. This is actually the general solution for the heat conduction equation, but which is this, dot square t del x square equal to 0. This is the heat conduction equation in a one-dimensional without heat generation and under steady state condition, so that the general solution of this equation is this. Okay. Now we will make the following. Okay. After we derive the temperature distribution, okay, in the Cartesian coordinate for the assumption that we make, which is under a steady state one dimension, then we obtain the temperature distribution, which is this. This equation actually illustrates that the temperature distribution here is governed by this equation, okay? So that if we want to find the temperature here, okay, at any point, this is x equal to 0, okay, till x equal to L. For example, if we have the length is 1 meter, for example, then at any distance here, we can find the temperature, okay? All we have to do is to measure the temperature at T1 and T2, okay? We can measure them, okay? And after that, we can find at any point of x, okay, then temperature at x will be found easily. Okay, this is called the theoretical temperature value. We can install thermocouple or any temperature recorder in order to find the measured temperature, and we can make the comparison between the temperature taken from the experimental data and temperature from equation, which is this equation. And we can make a comparison between each curve in order to find the temperature error in the measurement of the thermocouple. And the relation here is actually linear, because this is not x squared, okay? So that the temperature will drop, as I illustrated before, okay? The temperature relation here is linear, okay? Because the temperature drop here linearly according to this equation. You can't do this experiment in the laboratory, which is very easy. Now, let us complete. As I illustrate, we are in the heat transfer subject. We are interested in temperature and also in the heat transfer. This is our concern. So that this is a blade, for example, as I illustrated. Now let us apply the heat conduction law, which is governing by the Fourier's law, which is very important. So that Q minus K a dt by dx. Now all I have to make now Q equal minus K A, okay, d by dx for the temperature distribution, which is this. So that I will substitute this equation here. This equation can be substituted here. So that here I have T2 minus T1 divided by L multiplied by x plus T1. Now this is T1 and this is T2. This is here x equal to 0, x equal to L. And this is can be derived easily, okay? And this is easily derived, so that minus K A. This is the derivative is 0 because it is constant. And when I derive this equation corresponding to x, this equation actually d by dx, T2 and T1 and L, all these are constant because L is a constant because it is the length of the plate, and T2 and T1 actually also constant. They have some value, for example 100 Celsius and 25 Celsius. They are constant, so that when I derive them, they will be out of the derivative sign, so that d by dx for x will be 1, so that T2 minus T1 divided by L. Now I can write the following. The heat equation will be, after I distribute the negative sign here, I will have T1 minus T2 multiplied by Ka divided by L. Now this can be written also T1 minus T2. This will be as a denominator here, L divided by Ka. I hope that this is clear. All I have to make here is that I transfer and move Ka here divided, so that I make L divided by Ka. And the reason for this movement and the transfer and write L divided by Ka, because L divided by Ka is very important symbol in the heat transfer literature, okay, because T1 minus T2. L divided by Ka is defined as R sub Th, okay, which is the thermal resistance of the conduction. So that the thermal resistance of a plane wall will be its length divided by the thermal conductivity of the material multiplying by the area. So that if I have a plane wall, okay, so that the thermal resistance of this wall will be its length, okay, for example, it has some length, for example, 45 millimeter, divided by the thermal conductivity of this material multiplied by the area, but here the area is not L, for example, let us this H. The area here is not L by H. No, actually the area here will be this. Okay, as I illustrate, we consider heat in one-dimensional only, so that the area here will be the cross-sectional area that make an angle 90 degree with the flow direction, which is very important, as I illustrated in the previous example in lecture 1, and I will illustrate it very soon. So that now we find that the thermal resistance is L divided by Ka, okay, and Q is T1 minus T2 divided by RTH. This is actually very important law, okay, so that this equation is the heat transfer that for one-dimensional heat conduction equation, okay, for this general solution for this equation, okay. Now let us complete. This is actually only one wall. Then what we have, or what? How can we calculate the heat transfer? Heat transfer if we have composite wall, okay? If we have more than one wall, for example, if we have only one wall, then it have some length, for example, and it have T1 here and T2 here, and have some thermal conductivity, then it is very important, very easy to find the heat transfer flow across this wall, which is T1 minus T2, okay, T1 minus T2 divided by L divided by Ka, okay. L is the length of the plate. We have some value, okay, for example, let us, this is 100 Celsius, this is 25 degrees Celsius, so that 100 minus 25 divided by the length of the plate, let us 1 millimeter, so that it will be 0.001, okay, I transfer millimeter in meter, divided by thermal conductivity, let us 375, multiplied by the area, let us assume that we will find the heat flux, so that we have Q divided by area, so that I will find the value as I illustrated in the previous lecture, watt per meter squared, and we denoted this as a heat flux. This is actually very simple if we have one plane wall. Then what? How can we calculate this Q, heat transfer or heat flux for composite wall? Now, if we have more than one walls, okay, so that let us draw very simple schematic representation of this problem. Let us say that we have a composite wall. This is wall A, and this is wall B, and this is wall C. Of course, for each wall have its own thermal conductivity. The thermal conductivity of this wall is different from wall B, and they are both different from wall C, which so that KB and C, each wall have its own thermal conductivity, and each wall have its own thickness. Here L sub A, thickness of B, and thickness of C. Now, as we learn that the temperature actually drop, for example, this is T1, so that it will be drop further and further, okay? The temperature drop and the physical reason behind this, the reduction in the temperature actually due to the particle of the fluid or molecules inside this wall actually resist the heat direction, the heat flow, so that we will get a temperature gradient. So that let us, this is T2, this will be T3, and this is T4. Now we make a very important assumption, which is the heat transfer actually across this wall, and this wall and this wall are constant, so that the heat transfer Q during A equal to the heat transfer through B and through C. It will be constant. Now, based on this fact, I can write, actually let us remember that the heat transfer actually is delta T, okay, or delta T, yes, divided by L divided by Ka. So that I will write the following. Q will be, this is Q through this wall will be T1 minus T2, okay, as I illustrated, T1 minus T2 divided by the length between these two walls. So that Q will be T1 minus T2 divided by the thermal resistance of this wall, which is L, okay, of A divided by K of A multiplied by the area. We will assume here the area is constant, okay, and this is equal to the heat transfer through the wall B, which is T2 minus T3, okay, divided by the thermal resistance here, T2 minus T3 divided by the length of B divided by K of B area, and this is equal to the heat transfer through wall C, which is T3 minus T4 divided by L Ka for wall C. And this thing we illustrate that. Now we will make the following, okay? This is actually can be written like this, T1 minus T2 equal to, actually we will illustrate and treat with this, okay? I can transfer this term to another, so that this will be Q L A divided by Ka A. I mean, this is actually here, length of A, okay? Beside that, I will treat this with the Q, so that T2 minus T3 will be Q multiplied by the length of the wall B divided by K of V multiplied by the area. Finally, T3 minus T4 will be, we will treat this T3 minus T4 divided by this. This is equal to Q, okay, so that I transfer this to another side till I get a Q LC divided by K of CA. Now I have three equations actually. I have this equation, and this equation, and this. Okay, so that all I have to do now is that I will add each equation to another. Okay, so that if I added them, then I will get the following: T1 minus T2 plus T2 minus T3 plus T3 minus T4 equal to, we illustrate that the heat transfer Q, which is Q, is constant through the composite wall, so that I can take it as a common parameter. And here I have L of A divided by Ka multiplied by the area, okay, plus L of B divided by thermal conductivity of B multiplied by the area, plus L of C divided by K of C multiplied by the area. Now, after that, we will do the following. You can see that we can reduce and cancel some parameter. This is minus T2 plus T2, so that can be cancelled. T3 minus and plus, so that can be cancelled. And this way, we get T1 minus T4, okay, equal to a Q multiplied by L of A divided by K of AA, plus the length of wall B divided by K of B, A, plus L of C divided by K of CA. Now I can write in terms of a Q, so that a Q will be T1 minus T4, okay? T1 minus T4 divided by LA divided by KA, plus L of B divided by K of BA, plus L of C divided by K of CA. Now, if you remember, I tell you that if you remember here, that the length of the wall divided by its thermal conductivity multiplied by the cross-sectional area is nothing but the thermal resistance. Okay, so that I can write that Q equal to T1 minus T4 divided by R thermal of A, okay, plus thermal resistance of wall B plus thermal resistance of wall C. Okay, because we have a three wall. Okay, in this way we can see that if we have a plain wall, then it is very easy to obtain a general formula for calculation of heat transfer through the composite wall, which is if we have actually, as I illustrated, we have this, okay, wall A, B and C. This is half LA, and this thickness is L sub B, and this is L sub C. Okay, I hope my schematic representation of the problem is clear for you, and each material have its own length, K of C, and the heat transfer is constant through each wall. Okay, and we say that this is T1 and T2, T3 and T4. In this way you can see that if you have a composite wall and you want to find the heat transfer through this wall, then all you have to do is to write the temperature at the sides T1 and this is T4. Okay, it is not important to dealing with the T2 and T3. You should focus about T1 and T4, okay, which is the temperature at the boundaries of the wall, so that you can see T1 minus T4 divided by the thermal resistance of each wall, as I write here, thermal resistance of A plus thermal resistance of B and C. Okay, so that we can generalize the equation for the composite wall and write that Q equal to T1 minus T n plus 1 divided by summation with L divided by Ka, okay? L divided by Ka, which is the thermal resistance, from 1 to n, okay? And actually n is a wall. Okay, for example, if we have here, the number of wall here is 3, okay? Because we have this wall number 1, wall number 2, wall number 3. Okay, so that here n is 3. In this way we can write that Q will be T1, which is the temperature here, minus T n plus 1, n here is 3, so that we have 3 plus 1 is 4, okay, as I write it here, okay, divided by summation from 1 to n for L divided by Ka, okay, from 1 to n is 3, so that I will write L divided by Ka for 1 plus L divided by Ka for wall 2 plus L divided by Ka for wall 3, okay, as I mentioned here, okay. So that this is a general formula for the heat transfer through a composite wall. But we should keep in our mind, and this is actually very important, there is no thermal resistance here between the walls, okay, because the temperature through the wall actually is a drop, is not like this. I will illustrate it soon, because if we have a composite wall, then there is a thermal resistance, and the problem here will be different, okay, because the temperature here, we illustrate the temperature between wall A and B is a constant, but there is some case study, the temperature here, if I have T1, then this is T2 and this is T3. Okay, so that this will be different here, because we should include another term here, which is the thermal resistance contact. Okay, so that I will illustrate it very soon. So that this equation actually valid for the conduction heat transfer for a composite wall. Now, after we complete this type of the heat transfer, let us treat with another case study, which is if we have a thermal resistance, okay, contact in a plane wall, so that it will be actually not different so much, because all we have to do is to add this thermal resistance, so that if I have, for example, if I have this composite wall, okay, this wall of two walls, okay, wall A and wall B, and let us write that this is T1, okay, this is T2, okay. There is thermal resistance. Actually, this concept is very important. Thermal resistance, okay. Thermal resistance between the walls, okay. Thermal contact resistance, which is between the walls, okay. Then T2 here, and this will be T3. Then so that you can see, it will be dropped something like this, okay, T4. Now when we write the heat equation in order to find the heat transfer, all we have to do is to write Q equal to the delta T divided by summation R thermal, and this will be delta T divided by AL divided by KA, okay, for wall A, plus this wall, okay, L divided by Ka for wall B, plus the thermal resistance here, which is actually, and sometime it is given for you, okay, so that you should keep, you would be focused on this value, okay, when it is mentioned for you. If there is thermal resistance between the wall, then it is very important to include this, which is thermal resistance, okay, between the surface A and B, which is the contact thermal resistance, okay. You should include it. And delta T here will be T1 minus T4, okay. Now after that, we till this moment we complete this concept of the plane wall and composite wall. Now let us discuss with some topic which is very important in the heat transfer. Actually, we illustrate that if temperature T1 and T2 are isotherm, which they are constant, okay, there is no fluid here, okay. Some application in the heat transfer, we have a fluid environment, so that if I have a plane wall, okay, but I have here some fluid, okay. This is, for example, T1 and this is T2, okay. This is a plane wall, have some thickness and thermal conductivity, okay. But we have here hot fluid, okay, hot fluid, okay. This is hot fluid, and as you know, the temperature will drop, so that the fluid environment here will be relatively lower than that, so that I write it TCF, which is cold fluid, okay. And I want to find the heat transfer through this case study. Then all you have to do is to make a thermal resistance or a thermal resistance schematic diagram, okay. This can be written like this, okay. Now this is thermal resistance, okay. We actually can make the following, the same techniques as I illustrated here. Maybe it is not clear for you. Actually, I draw this, okay, but maybe it's not clear. We made heat transfer with electricity, and we make some analogous, okay, so that we write this resistance, okay, which is very important in the conduction heat transfer. So that here, this is the actually the thermal resistance in the conduction is L divided by Ka in the conduction, okay. But for the convection, then the thermal resistance for the convection will be different. Will be 1 divided by the heat transfer coefficient multiplied by the area, which is the area, okay. Now H actually is the heat transfer coefficient, okay. As we have K, which is the thermal conductivity, H is very important concept in the heat transfer literature, which is the heat transfer coefficient, okay. So that here we have 1 divided by H of the hot fluid. K actually is special for the metals, while H is for fluid, okay. And here, this is the 1 divided by H of the cold fluid multiplied by the area. Now let me show you the following. In the heat transfer, we illustrate the heat transfer, which is the Q, and the conduction can be obtained from the Fourier's law, which is minus K A dt by dx, okay. while for convection environment, then the heat transfer can be written from this law, HA delta T. Okay, the heat transfer and the convection equal to the HA delta T. Okay, now if we want to find the units of the heat transfer, okay, of the heat transfer coefficient, we can use this. Okay, H equal to the Q divided by A delta T. Now, we know the unit of the heat transfer is watt, the unit of area is meter square, and the unit of temperature is Celsius. In this way, the unit of H is watt per meter square Celsius, okay? While, if you remember, the unit of the thermal conductivity is watt per meter Celsius, the unit of the heat transfer coefficient is watt per meter square, okay? This is the major difference, okay? This is for the solid, and this is for the fluid. We use H when we have some fluid, okay? In this way, we can develop the heat transfer through this environment, which is we have here solid, okay, material, and here we have a fluid layer, two fluid layers, which they are hot fluid and cold fluid. And we can, using the similar techniques that we just use it, okay, which is this. Okay, now the heat transfer Q equal to through the solid is T1 minus T2 divided by the thermal resistance between them, which is IL divided by Ka. Now we have actually here two fluid environment, okay, so that Q equal to H of the hot fluid area T of the hot fluid minus T1, okay? We're dealing with this. This is hot fluid and this is T1, so that T hot fluid minus T1, okay? Multiplied by the area multiplied by H of the hot fluid. And Q of the, this is for the for this layer, okay? For this and this, will be H sub Cf, which is the heat transfer coefficient of the cold fluid multiplied by the area multiplied by T2 minus TCF, okay? T2 minus T cold fluid, okay? So that we start from this. After that, we find the heat transfer through the conduction and find the heat transfer through the convection, okay, between this solid and this fluid layer. Now, we can write that, okay? We can write, for example, let us start by this, okay? T hot fluid minus T1. I will transfer hot fluid, okay? This is actually here, hot fluid. Transfer this term to another, so that I will write Q divided by H of the hot fluid multiplied by the area. And similarly, T1 minus T2, which is this, equal to QL divided by Ka. Finally, T2 minus T cold fluid will be the Q heat transfer coefficient of the cold fluid layer multiplied by the area for this, okay? T2 minus TCF is the Q divided by this. After that, we will add this equation, and when we added this equation, you can see that this T1 will be cancelled with this, T2 with 2, till we get T of the hot fluid minus T of the cold fluid equal to a Q is constant, so that it will be taken as a common, multiplied by 1 over the heat transfer coefficient of the hot fluid multiplied by the area plus L divided by Ka plus 1 divided by H of the cold fluid area. Now we have the following, okay? The area is constant, so that it can be transferred to the top of the environment if I want to find the Q, because this is my first quantity that I want to find it, so that this will be T of the hot fluid minus T of the cold fluid, okay? However, we will keep it here, divided by summation R, thermal. And this is R here, mean the resistance due to the conduction plus resistance due to the convection. And the resistance of the conduction is, which is applied for a plane wall, okay? Have some thickness and some thermal conductivity is L divided by Ka, while the the resistance of the convection will be when divided by the heat transfer multiplied by the area. In this way, we develop the heat transfer if we have a fluid layer attached to the solid material. Okay, this is an equation actually. This formula, okay, is valid for this. If we have solid material and attached to this solid material two fluid layer on both sides. Okay, I hope that this is clear. So that let us develop some important quantity. Okay, we say that we have thermal conductivity, which is K, and we have H, and we have thermal resistance. Okay, so that we get to this equation, a Q equal to T hot fluid minus T cold fluid divided by L divided 1 divided by H of the hot fluid plus this is 1, okay, plus L divided by K, this is area, Ka plus 1 divided by H of the cold fluid multiplied by the area. Now the area is constant, so that it can be taken as a common and transferred to the denominator, so that the Q will be area multiplied by T hot fluid minus T cold fluid divided by 1 over HF of the hot fluid plus L divided by K plus 1 over H of the cold fluid. Now these actually known as overall heat transfer coefficient, U, which is 1 over H of the hot fluid plus L divided by K plus 1 divided by H of the cold fluid. This is called as overall heat transfer coefficient. Okay? So that in this lecture we illustrate the derivation of the heat conduction equation and what is the possibilities that we can make it and assumption in order to simplify the equation as much as possible. And after that we include the concept of the thermal resistance and how can we illustrate and calculate the heat transfer through a plain wall and through a composite wall. Beside that, we take, if we have a solid material, but there is some fluid attached to this material, to this solid material. If we have a fluid environment, okay, hot and cold, and how can we calculate the heat transfer? And the most important thing and the most assumption that we make it is that the heat transfer through the wall, through this convection, remain the same in order to make the simplification as much easy as possible. I hope it is clear. In the next lecture, we take a mathematical and solve example that cover this topic, okay, in the first lecture, in the next lecture, which is about the thermal resistance and thermal contact, okay, because if we have a composite wall, but the temperature will drop here, okay, due to the contact between wall A and B, because you know that will make some loss in the heat transfer. So this will be illustrated in the next lecture of the heat transfer. Thank you very much.